Hey guys, so looking over module 9, I know some people already asked about number 13, and so when I look at it more, I'm not going to be actually counting it for your homework, but I am making this video just so I can go over the problem because I still think that this is important to know either way. So this is number 13 in module 9 on page 195, and so this problem tells you that you have 0.25 moles of H2, 0.25 moles of I2 in a 1 liter flask, and that the Kc is 54.3, and that this is the general expression. And so overall, they want to find the concentrations at equilibrium for each one of them. And so what we're going to have to do first is make sure that we convert from moles, right? Moles to molarity. So remember that the molarity formula is moles divided by liters. And so it is a 1 liter flask. So anything divided by 1 is going to be the same. So essentially H2 and I2, which have the same type of moles, are going to be just 0.25 molarity. And so now we know the initial concentrations for both of these. And so now let's do the ice table, where it's H2 plus I2 is going to 2HI. And so always just double check if it's balanced, which in this case it is. And so remember, I stands for initial, C stands for change, and E stands for equilibrium. And so we make this little chart. So we know the initial concentrations of H2, which is 0.25, and I2. And then for H2, they didn't give us any value, so we could just assume that it's going to be 0. And so for change, since H2 and I2 are being consumed, it's going to be minus, while the products are being made, so plus. And so we're going to have our x's, but to know how much x's we're going to have is by looking at the coefficients. So this is 1 and 1. So this can be the same as either minus 1x or just minus x. It's the same thing. And over here, since it does have a 2, it'll be plus 2x. And so in E, we're going to combine both I and C. So this is going to be 0.25 minus x, 0.25 minus x, and 0 plus 2x is just the same as 2x. And so we're going to input these values into the Kc expression. And so we do actually know the Kc value, which is 54.3. And so this is equal to 2x. So remember, this is Hi. And remember, Hi to the power of 2. Divided by 0.25 minus x multiplied times 0.25 minus x. And remember, I just got these values because just as the general expression is Hi squared divided by H2 and I2. So that's how I got it. All we did was just input these with this column right here. And so we're trying to find what x is because we're trying to find the equilibrium concentrations, and we can't actually calculate them until we find x. And so we are going to have to isolate it. So to isolate it, we're going to have to use the quadratic formula, which is x is equal to minus b plus minus the square root of b squared minus 4ac divided by 2a. Whew, that was a mouthful. All right, and so in order to find out which one's a, c, and b, the general expression is ax squared plus bx plus c is equal to 0. So essentially what we're going to have to do is that we're going to have to take this whole equation and make it look like this. And so I'm going to be doing that onto, sorry, actually I have some space here already. Okay, so first, let's try to break up this fraction to make it a little bit more simpler. So since this is being divided, we're going to multiply all of this to the other side. So it's going to look like 0.25 minus x, 0.25 minus x is being multiplied times 54.3 is equal to 2x squared. And remember, sorry, this is parentheses. Remember algebra, right? So this should be 4x squared because 2 to the power 2 is 4. And then x squared. So 4x squared is equal to all of that. And so for the next problem, we're going to be just concentrating on these two first before we move on. And so I'm going to do that on the next page. So we have 54 over here on the side. Let's not forget about it. But for now, we're going to focus on 0.25 minus x multiplied times 0.25 minus x. And so I'm not too sure what they call it. but I'm pretty sure I think in algebra they kind of taught you this method is like, first you go here, so 0.25 multiplied times 0.25. So I'm going to put that in my calculator. Should be 0.0625. So 0.25 multiplied times minus x should be minus 0.25x. So what about minus x multiplied by 0.25 should be minus 0.25x. And lastly, minus x multiplied times minus x is just going to be x squared. So now let's add these up. And so minus 0.25 minus 0.25 should be, I believe a minus 5 minus 0.25x. Then we have that x2. So that's the same as x2 minus 0.5x plus 0.0625. So that's what we got for all of this. But remember that we still have that 54.3 we have on the side. So now let's multiply everything times 54.3. So this is going to be 54.3x squared minus 27.15x plus 54.3 times 0.0625 is going to be about 3.4. I'm just rounding up. So now we have this whole thing, and remember the other side, we have that 4x squared. So remember, we want this formula of ax squared plus bx plus c is equal to 0. So we need to get this out of the way. So minus 4x squared. So 54.3 minus 4, oh no, I did it wrong. 54.3 minus 4 should be about 50.3x squared minus 27.15x plus 3.4 is equal to 0. So finally we have our A, our B, and our C. So now we can input that into the quadratic formula. And so remember, it's going to be x is equal to minus b plus minus the square root of b squared plus 4ac divided by 2a. So now let's just input these. So minus 27.15 plus or minus the square root of 27.15 squared plus 4 times 50.3 times c, which in this case is 3.4, all divided by 2a, which is 50.3. And so try to put that into your formula. And so you should come up with two different values, and that's because of this plus and minus. You're going to do one with plus and then another all with just minus. So for one of them, it should be 0.196. And so that's going to be your right answer. And so now what you're going to do is that from long ago, we had this chart, and now we know where our x is, which is 0.196. And so now we're going to input it into each one of those. So 0.25 minus 0.196 is going to be 0.054. And then 2 times 0.196 is going to be 0.392. And so what we just found altogether was that for H2, which is the same as I2, both at equilibrium, that it's going to equal to 0.054. And that for HI at equilibrium, it's going to be at 0.392. And that's going to be your final answer for number 13. And so as you kind of noticed, I said that there's going to be two answers. And so the other answer is actually 0.343. And so the only reason why I didn't choose this one is that when you're looking at the equation over here, it wouldn't make sense to be 0.25 minus 0.343, because then you're going to come out with a negative number. So that's why when you're doing the quadratic formula, sometimes it's easy because one is plus and one's a negative number, so you choose the positive one. But in this case, both of them were positive, so we went with 0.196 because it just made more sense for the answer as well. So in the end, this should be your answers for number 13. Just to kind of go over like what we did real quick. So what we did first is that we converted moles to molarity, and then we did the ICE table, and from there we inputted all these values into the K equation. And since we're trying to find X, we did the quadratic formula. And so from the quadratic formula, we found that X was equal to 0.196. And from there, we inserted into all these values, and we're able to find the equilibrium concentration. And so just know that you're only using the quadratic formula. Here, let me do it on another page. So you only use the quadratic formula of when the K value is something very big. Okay. However, as you're going to kind of see, and we're going to kind of talk more into other modules, if the K value has something of times 10 to the power of, let's say, -5 or smaller, like -6 or -10, that's such a small number that it's going to be pretty insignificant. So that's why I think previously on other ICE tables, we would just neglect the -x. But in this case, we can't neglect the -x because Kc is such a big value of 54.3. And that's how we had to go that route. So if this was actually a smaller number, this would have been just much more simpler because you would just have, let's say, 0.25 multiplying times 0.25 and so forth. And it would be much easier to find X or so forth. But because it was just also a big value, that's another reason why we had to use the quadratic formula. But at the end of the day, if you still have more questions about number 13, just please contact me. But I hope this helped you out. Other than that, have a good day.